Hi everyone, we are here to explain the ML algorithm of our project Smart Campus Navigation System. Here is a brief explanation of each import in the code. Import pandas as PD. Purpose: it is used for data manipulation and analysis. Common tasks: reading datasets like CSV files, handling missing data, filtering, grouping, and transforming data using data frames. Import matplotlib.py plot as PLT. Purpose: used for creating basic plots and visualization. Common plots, line plots, bar charts, histograms, scatter plots, etc. PLT, a common alias to use its function more conveniently. Import Seaborn as SNS. Purpose: built on the top of Matplotlib. Seaborn provides more attractive and informative statistical graphics. Common features: beautiful default styles, functions for heap maps, coloration matrices, categorical plots, and better integration with pandas. Together, these libraries help in exploring, analyzing, and visualizing data effectively in Python. df is equals to pd.read CSV content geometry navigation sample CSV pd.read CSV. This is a panda function used to read a CSV file and load it into a data frame. Content GMIT navigation sample.csv. This is a file path to the CSV file. In this case, it looks like being run in Google Colab, where files are often loaded from the content dictionary. df is this variable stores resulting data frame, allowing you to manipulate or analyze the data using pandas function. In short, this line reads the data from a CSV file and stores it in a table-like structure for further analysis. df.add. This is our data frame which contains the data loaded from the CSV file. Head. This is a pandas method that runs the first 5 rows of the data frame by default. Purpose: it's commonly used to quickly preview the data set and understand its structure, including column names, data types, sample values. You can also pass a number to head to get more rows. Print missing values dot is null dot sum. Here is a breakdown of this line. df.e is null. This creates a data frame of the shape as df, but the true values and the false for non-missing values. Dot sum. When applied to a Boolean data frame, it counts the number of true values. Print missing values. This prints the result with a label missing values, and the output will show how many missing values are in each column of the dataset. Example output: missing values. Column 1, 0. Column 2, 3. Column 3, 1. D-type int64. Next will be continued by Likita.
Import pandas as PD. Pandas is a library used to work with tabular data like spreadsheet. Reading the SCV file. This loads the data from SCV files named location into a data frame called df, printing column names and first few rows. df column shows the name of the columns in your SCV files. df head shows the first 5 rows of the data so you can preview what's inside. Importing KMeans and standard scalar. KMeans is a clustering algorithm that groups similar data points together. Standard scalar is used to normalize or scale the data so that all features have the same importance. Selecting the latitude and longitude. This picks only the latitude and longitude columns from your data for clustering. Scaling the data. Standard scalars create a scalar object. File transformer scales the latitude and longitude so their values are standardized, means 0, standard deviations 1. This helps the K-means algorithm perform better. Next will continue by Lakshmi.
K-means n cluster is equal to 5. This creates a K-means model that tries to divide the data into 5 clusters. Random state is equal to 42. This ensures consist result each time the code runs by setting a fixed seed. Fit predict x scaled. This fits the model to scale data x scaled and assigns each data point to a cluster. df cluster. We store the cluster label in a new column called cluster in our data frame. This helps us to group similar data points together for further analysis and visualization. Sometimes column names may accidentally print df.columns. It will print the columns. df columns is equal to df columns dot str. This code sometimes columns names may accidentally include spaces, example age instead of age, which can cause errors or make it harder to reference them in code. .str.strip cleans up these columns names. Print df.column. It is used to verify the cleanup was successful. This is good data cleaning step to ensure column names are consistent and easy to work with. Next will be continued by Nisha.
This code checks if the column, location, 4 and cluster all exist in the data frame df. If all the three columns are present, it prints the first 5 rows of those columns. If any of the columns are missing, it prints a message saying that one or more required columns are missing. This code import pandas as PD from sklearn preprocessing, import standard scalar from sklearn cluster, import KM. Import libraries pandas for data handling, standard scalar and KMeans for clustering, and metapolite lab provide for floating. Upload a CVS file using Google Colab file upload tool. Loads the upload CSV into a data frame called df. Strips white space from column name to ensure they are clean and consistent. Require colon location. This code checks if all requirement columns, location, floor, latitude, longitude are present in the data frame df. If any column is missing, it raises a key error with a message like missing column latitude. This ensures the dataset has all the necessary data before continuing. Next will be continued by Shreya B. Yadav.
X is equal to df latitude longitude extracts the geospatial features into X isolating variables relevant for clustering. Scalar is equal to standard scalar, which initializes a standard scalar to normalize data, zero mean unit variance, vital for distance-based algorithms like K-means. X is equal to scaled is equal to scalar dot fit transform of X, which means fits the scalar on X and transform it ensures both latitude and longitude contribute equally to distance calculations. And applying K-means is equal to K-means, n cluster is equal to 4, random state is equals to 42. Instantiates K-means with 4 clusters and a fixed random state for reproducibility, logs randomness for consistent results. DF cluster is equal to K-means dot fit predict X scaled. It performs a clustering on scaled data, assigns each point to a cluster and stores the result in a new custom cluster column, making the segmentation actionable. And next, plotting a graph of our project. PLT.figure of fixed size is equal to 10,6 and scattering it and plotting sets the canvas size of 10 into 6 inches for a clear wide visual layout. Scatter is equal to PLT.scatter of DF longitude, DF latitude. C is equal to DF cluster. It plots the points by longitude and latitude, colors them by cluster using the vivid rainbow color map, intuitive and engaging. PLT.x label of longitude labels the x-axis geographic content. PLT y label latitude labels the y-axis, complements the coordinate systems. PLT.title campus location cluster adds a title, gives meaning to the visualization. Grid is equal to true, add grid lines enhances readability and positioning. PLT.color bar scatter comma label is equal to cluster attaches a color legend, maps color to cluster IDs for interpretation. PLT.show renders the plot final output to the screen. And this is the output and the graph of our smart campus navigation. And next coming print DF location, floor, latitude, longitude cluster. It prints the output, the content to the console, visibility into your data. Location, floor, latitude, longitude cluster selects a precise slice of our data frame, only the most relevant columns. Location identifies the place like library, labs, classrooms, staff rooms. Floor content, contextual spatial dimension within buildings. Latitude and longitude geospatial coordinates. Cluster is the result of K-means, groups locations with spatial similarities. It gives a clean interpretable view of how physical locations are grouped algorithm. Insight made visibility. And the conclusion, we designed a smart campus navigation system by leveraging geospatial data and unsupervised machine learning by applying feature scaling and K-means clustering to latitude, longitude coordinates. We transformed raw location data into meaningful clusters, enabling intuitive zone-based campus segmentation. The result is the scalable, visually interpretable model that enhances wayfinding, supports congestion prediction, and lays the foundation for dynamic real-time navigation experiences. This project redefines the spatial intelligence on campus, setting the stage for the smarter data-driven infrastructure. Thank you.